Okay, so statistics, here we come. Yes, all right. Okay, has anyone already taken a statistics class? Oh, a few of you. Okay. And why are you taking this class again then, or?
It's been 20 years.
Oh, it's been a long time. Okay. Well, I hope this class will be good and put it into a context that makes sense. And maybe you liked your statistics class before, maybe you didn't. In either case, I hope you like this class. I hope you like me. That sounds so pathetic to say. I can't believe I just said that out loud. But anyway, here we go. All right, so statistics. What is statistics? Why do we study statistics? Okay. All right, and everyone can see that and read that? And we're good? Why do we study statistics? Okay, so I argue that we study statistics so we have a better understanding of the world around us. And in particular, all right, and in particular, statistics allow us to make conclusions from limited data, or depending on how you want to use the word statistics, statistics allows us, whether, is this plural or singular? It's a mystery, right? Okay, so statistics, the subject, allows us to make conclusions from limited data. All right, so what do I mean by that? Making conclusions from limited data. So here is one example. So when you read your textbook this week, and if you don't have the textbook, go out and buy the textbook. You probably qualify for a trial membership of Amazon Student, which is great. I love Amazon Prime and their whatever. And you can get the shipping for 2-day shipping for free, so you can get it. So when we say making conclusions from limited data, this is what I mean. So generally, we have some kind of research question. Okay, so we may have a research question, and here's an example from the textbook. And this is, does exposure to E. coli bacteria increase the incidence rate of liver tumors in mice? Okay, so some researchers had this question. They said, you know, if we expose mice to E. coli bacteria, does it cause liver tumors at an increased rate in the mice? Okay, and so they gathered some data, and this is what the data looked like. Okay. All right, so we have those mice that were exposed to E. coli, and we had mice that were kept in a germ-free environment. And we had a total of 13 mice exposed to E. coli, and a total of 49 mice kept in a germ-free environment. Okay, and then some of them, and so all of these mice, you know, they lived in these living situations, and then the researchers killed all of them at the end, and they cut open the mice, and then they said, oh, well, these ones developed liver tumors, and these ones did not. Okay, so some have liver tumors and others have no tumors. No liver tumors, I should say. All right, and so in the E. coli environment, 8 out of the 13 developed liver tumors. Let me just write that over here. And 5 did not. In the germ-free environment, 19 developed liver tumors and 30 did not. Okay? And so the question is, does exposure to E. coli bacteria increase the incidence rate of liver tumors in mice? Okay, and the question, when we ask this question, we're not really interested in knowing, well, for the mice that we used, okay, because the answer is, you know, for the 49 mice here, you know, if we do 19 divided by 39, or I'm sorry, 19 divided by 49, that percentage is 39%, okay? And so 39% of mice in the germ-free environment developed liver tumors, whereas in the E. coli environment, if I do 8 out of 13, 62% of the mice developed liver tumors, okay? And the question really isn't, okay, for these 13 mice, was the development of liver tumors different for these mice? Because the answer is yes. 62% of these mice did, and 39% of these mice did, okay? That's not really the question. We want to know, well, could this be generalized to all mice potentially, okay? Could we say for all mice, does that mean exposure to E. coli increases the incidence of liver tumors, and then possibly if it does for all mice, you know, what does that say about E. coli and people, or E. coli and, you know, just life in general and things like that? You know, we generally want to generalize the conclusions of our question to what we would say the population, or all mice, okay? So usually we are not interested in only the specimens or subjects we study. We often want to generalize our conclusion to the population, okay? And the population, so here's a definition, the population would then be every single person or every single thing that is relevant to the research question that we have, okay? The population is everyone or everything relevant to our research question. So in this question, does exposure to E. coli bacteria increase the incidence rate of liver tumors in mice? The population, okay, would be all mice, okay? All mice possible, okay? Because we want to know, does E. coli, you know, would this have an effect to all mice? Could this effect be generalized to all mice, okay? So, if we did this experiment and we looked at this data, what would you guys say? Does it look like E. coli increases the incidence rate of liver tumors in mice? Maybe, maybe not. I don't know. We have someone saying something.
I was going to say that maybe the sample size kind of leads to a not good enough grouping.
Yeah, okay. So we have some issues with the sample size. Okay, so wait, have you taken statistics before? Okay, so you're using technical terms like samples. Oh, well, it's not that technical, but you're using things like sample size, which would indicate that you've probably taken statistics before, or at least exposed to this. So you know, maybe in junior high or high school, we would say 62%, we would say, you know, what percentage of mice developed liver tumors? And you'd say 8 out of 13, 62% over here versus 19 out of 49, 39% over here. And we might say, oh, 62% is bigger than 39%, so it seems that E. coli increases the rate of liver tumors, and that increase seems to be about 23 percentage points, something like that, okay? Well, there's a question, of did we look at enough mice? Is our sample size, or is the number of mice we looked at, is that enough to make meaningful conclusions? That is a legitimate concern, okay? Did we look at enough mice? Okay, and so, that is our sample size large enough? That's essentially what that question is. All right, and we would have to do some kind of study there. But really, what it comes down to is, what if someone said, okay, at the beginning of the experiment, let's say we had a total of 62 mice, and that means a total of 27 developed liver tumors and a total of 35 did not, okay? We have 62 mice total. Let's say at the beginning of the experiment, let's say E. coli and the germ-free environment actually have nothing to do with liver tumors. Or let's just say we actually just had one room that was labeled room A and the other one was labeled room B. And there was no difference between these two rooms, and we kept 49 in room B and 13 in room A, okay? And let's just say at the beginning there were 62 mice, and 27 of these mice were, quote, destined to develop liver tumors anyway. What we did had nothing to do with whether or not liver tumors developed. Okay, let me just copy this little, so we'll save this, and we'll make a new slide, and put this over here. All right, so let's just say, imagine that at the beginning of our experiment, we have 62 mice, and let's say 27 of them are destined to develop liver tumors. Okay? And we're actually just going to just put them into two rooms that have different labels, and nothing actually should make a difference. Okay? Nothing about these living conditions should make a difference, but 27 of these mice were destined to develop liver tumors. Is it possible that just from randomly putting in the mice into the different rooms, that 8 of these 27 mice ended up in this one room, and 19 of them ended up in this room? Is that possible? Yeah, that's certainly possible. And the question is, well, how likely is that to happen? If it happens quite a bit, then the results we see here may actually just be a result of the random fluctuations or the random assignment process, and may not actually have anything to do with E. coli. If it turns out that it's possible, but it's incredibly rare, that it's incredibly unlikely for 8 to end up over here and 19 of these 27 liver tumor mice end up over here, if it turns out that it's very unlikely, then we would have an idea that, okay, even though it's technically possible to happen by random chance, because it's so unlikely to happen, our conclusion is that probably the living situation of E. coli had something to do with the development of liver tumors. Okay, does that line of thinking make sense? Okay, so let me just write that down, and I'm going to say, well, that's pretty much what statistics is all about. Okay, so we will say, what did I write? Are destined to develop liver tumors. Okay. It is then hypothetically possible that 8 of these liver tumor destined mice end up in one room and 19 end up in the other. In that case, the difference in liver tumor development is just a result of the random room assignments. Okay? We would want to do a study to see how likely this random result could happen. Okay? If it is quite possible, meaning the probability is high, then our results of our experiment, of the experiment, could have happened by random chance. Okay? If it is unlikely, then we would have reason to believe that the results of our experiment is not from random chance alone, but has something to do with the E. coli. Okay. Can you guys read my handwriting? I know I'm like writing it quickly, but I hope it's legible enough. And if you have any trouble reading it, reading the stuff up there, just raise your hand. Give you a moment to copy that down. Okay. Okay, so while you guys are finishing writing that up, that is essentially where we are headed in this course. Okay, we want to be able to ask these questions. You know, the data that we observed in our experiment, could this have happened from random chance alone, or is the more likely explanation that, you know, the difference between the groups is what's causing the difference that we observed. Okay. So as you read chapter 1 in your textbook, the first section just goes through a bunch of different scenarios that statistics kind of covers. Okay. So just maybe kind of a overview of our course. Okay. We're going to just start off maybe with just some, in today's lecture, we'll just start off with basics of data collection. Like very basic information about data collection, okay? Basics of data collection and basics of data description. So that's today's lecture. Okay. So we learn how to gather data and how to describe data using summary statistics and things like that. And then we have to learn probability and probability distributions. Probability distributions. Okay? And after learning the probability distributions, which takes a couple weeks, we learn, this goes into sampling distributions. Which is maybe an offshoot of probability distributions. And these come together into statistical inference. And statistical inference is all about making conclusions from limited data, right? Okay. We take our understanding about probability and sampling distributions and we compare that understanding to what we saw in the data, okay? When we describe our data, we take that and then we answer the question, how likely was our data to occur? Okay? And so, and the bulk of the class, so probably up to here, this will take us up to the midterm. Basics of data, probability distributions, sampling distributions, and then maybe just the very first thing of statistical inference, and that will get us to our midterm exam. After the midterm exam, we're just going to focus on a lot more methods of statistical inference, okay? And we get into like, just all the, many, it's more like a survey of the, many methods of statistical inference. Okay, and there are a lot of statistical methods, and we're just kind of going to say, okay, we're going to learn how to do this method, and we're going to learn how to do this method, and this method, and this method, and we're not going to go really deep into any one of these particular methods, but you'll be exposed to a bunch of different kinds, and they all apply in different situations depending on what kind of data you're dealing with. Okay, we have situations when you have categorical data and numeric data and this and that, and we've got all sorts of different things, and we're going to spend a bunch of time going over all of these methods. If you are going to do research in your future careers, there's a good chance that you'll need to go deeper into one of these statistical methods that we're covering. Okay, we're just going to cover kind of just like the basics of each of these different methods, and that's about it. I'm going to just say, oh, okay, and that's the course, right? It's 12 weeks. That's about all we can do. Chances are, if you do more statistics or more research, you're going to need to take a course devoted to one of these methods that goes a lot deeper. Okay, but in an intro class, we're just going to kind of do a survey of all of these different methods here. Okay. All right. So I think we'll enjoy. Well, I like teaching this class, and I hope you guys enjoy learning along the way. So let's go into the basics of data collection, and then we'll get into data description. Okay. So when it comes to data collection, we've got I guess we can talk about the types of evidence. All right. And the weakest kind, which we don't really call, is anecdotal evidence. Okay. And this is kind of like, these are the stories you hear, right? It's like, oh, you know, my aunt had this, you know, disease, and then she, I don't know, read something on the internet, and it said to swallow this stuff and do this thing, and she did it, and it worked, and she was cured. And you're like, oh, that's neat, okay? We call that anecdotal evidence. Without a kind of controlled study or things like that, it's hard to give credit to these types of anecdotes. It's not to discredit what these people experienced, and they certainly might have experienced you know, a cure for their disease, or you know, experienced some kind of interesting thing, but it's hard to assign it, I guess, scientific credibility, okay, without doing some kind of controlled experiment or observational study, okay? And so for statistics, we will deal with observational studies, and controlled experiments. And these are ways to gather evidence. Okay? With an observational study, we just observe. Or as much as we can, we try to just observe, okay? We try not to interfere with the subjects we study. Okay, other than taking measurements. And taking measurements in of themselves could have an effect on what you see, and that's called panel bias. So, for example, you know, somebody might come to your work and say, "Oh, I'm just going to observe what you do, and I'm just going to take notes on what you're doing. Don't mind me. Pretend I'm not here, and just go about your daily life or daily job." And we all know that on that day you are much less likely to slack off, and you are probably going to have be a bit more productive, or you know, maybe you're nervous, and so it affects your performance and things like that. So we have to take into account that measuring the subjects themselves may actually interfere with the measurements, but for the most part we try not to interfere with the subjects, okay? And we just, based on the data that we collect, we try to make observations and conclusions, okay? We try to make, our conclusions based on the data we collect. The problem is we cannot make cause and effect conclusions from observational data. Okay? Because when we have observational data, there may be confounding variables or lurking variables. Okay? There might be variables that we did not observe, variables that we did not gather, that are behind the cause and effect relationship. Okay? Might be other variables or factors. Behind the cause and effect relationship. Okay, so just a silly example. Okay, if you were to look at, well, this is not so true today, but maybe a decade ago. So let's say just in the 2000s, if you looked at different countries, and you measured cell phone usage versus life expectancy, what you would see is that countries that have high cell phone usage generally have higher life expectancy. Generally have. Okay. Does that mean cell phone usage is good for your health and causes you to live longer? No, we know that's not the case, okay? But using cell phones makes you live longer. Okay. And that's a silly example, and we know that what's going on is generally cell phone usage would be an indicator of maybe the infrastructure development of a country, and that generally means easier access to health care and clean water and things like that, and those are the things that impact life expectancy. But cell phone usage in of itself doesn't mean that using a cell phone is good for your health and makes you live longer. It's just that is related to these other things that do help people live longer. It's a little bit less true today because countries like in Africa have now widely adopted cell phones, and banking transactions are all done through mobile phone technology today. So so that's a good thing. But a decade ago, this is what you would have seen. This is a silly example. We know cell phones don't increase life expectancy, and so it's easy to see the flaw in this kind of conclusion of making a cause and effect thing. But a lot of times you'll see studies done today that are strictly observational, and people want to make cause and effect conclusions. And a lot of times people will share these links on the internet that will say, this and this, and you look at this and it seems like there's this, and they'll say, after this president took office, all of these other things happened, and therefore, this and that, and this, people will try to fit data to the story that they want to tell, and that may not necessarily be the true story that's going on. And so the rule of thumb is that from an observational study, you cannot make cause and effect conclusions. Now, this has been a difficult hurdle for a lot of researchers because we'll talk about experiments. From experiments, you can make cause and effect conclusions, but it might not always be possible to do an experiment. So people have long wanted to make conclusions from observational studies, and it's very difficult to do. And so at this level of our course, we're just going to say it's not possible, and that's what we're just going to say in this class. There are ways around it, but it requires a lot more, strategy and planning if you want to try to make a cause and effect conclusion from an observational study. This was actually how tobacco companies would try to say smoking had nothing to do with lung cancer, because to do an experiment, you would actually have to say these people are required to start smoking and these people are not required to start smoking, and there's ethical issues with that, and so that was not possible. And so tobacco companies for a long time would just say, you know, we find correlation between cigarette smoking and rates of lung cancer, but it doesn't necessarily mean there's a cause and effect conclusion. And it was actually difficult to argue against that. Today they have admitted that smoking increases the risk of lung cancer, but they still sell their cigarettes. Okay, so let's talk about controlled experiments. So controlled experiments, on the other hand, we ideally, and I will say ideally, we can control as many aspects of variation as possible in the subjects for our subjects. Okay, so ideally, so this is ideal. You know, I'm starting off all of these sentences with ideally. Ideally, maybe you have two treatment groups, or you have a few different treatments that you're interested in. You want to know, does this drug work and versus this drug? Okay, so ideally you have a few treatments, maybe two or more, few treatments, and the groups of subjects assigned to the different treatments are as identical or as nearly identical as possible. Well, as possible, and the conditions you know, that they're exposed to or that are applied are also identical. With the exception of the treatment. So that's a long sentence. Okay, but basically it's saying, let's say you want to know, does this drug help, you know, whatever it is that you're looking for, okay? So maybe you're trying to see if this is an effective drug for some ailment that people suffer. Ideally, you get a bunch of volunteers for this experiment, and maybe you have a placebo, and maybe you have the drug. And the two groups would be as identical as possible. The lives that they live, the diets that they eat, the amount of sleep that they get, all of these other things, the amount of stress that's in their life would be as identical as possible. The you know, the ethnic backgrounds or the racial backgrounds and the age and the genders of these two different groups would be as similar as possible, with the exception that this group gets the drug, the other group does not. Therefore, at the end of the experiment, if you see that the group that got the drug did better in terms of you know, whatever health measure that you're using versus the other group, you can say that the difference that you observed between the two groups can be attributed to the fact that this group got the drug and this group got the placebo. Okay, if you know, in non-ideal situations, okay, here's a silly example, but what if this group was all, you know, this group all ate I don't know, were on a vegetarian diet and this group was not, okay? And everybody on a vegetarian diet also got the drug, and everybody who was not on a vegetarian diet got the placebo, okay? Well, this would be a bad experiment because at the end of the study, let's say you find that this group that got the drug did better in terms of their health than the other group. Well, then you don't know if the difference between the groups is because they got the drug or if it's because of the vegetarian diet, okay? And so in that case, you would say the vegetarian diet is confounded with the treatment, and your study would not be useful because you don't know if the people have better health because of the vegetarian diet or the drug. And so in an experiment, you would make your two groups as identical as possible, including, genetic this and that and whatever. As much as possible, you do that, and then you can say, well, the only difference really between these two groups was the fact that this group got the drug, the other group got the placebo, and therefore the difference we see at the end of the day is due to the drug or the placebo. So that's the idea behind a controlled experiment. You're controlling as many aspects of variation as possible, and that way differences observed at the end of the experiment can be attributed to the different treatments. Okay, so we have tools to help us control these aspects of variation. Okay, well, one is random assignment. Okay, random assignment of treatments. Okay, we do not allow subjects to pick their own treatments. We assign them to the treatments. So we don't allow people to say, I want this, and because when people pick their own treatments, it could actually be an indicator of something else in their life, okay? The people who are on vegetarian diets are also, more likely to do this and that than they are, whatever, okay? I don't know. I'm talking generically here. So we have random assignment of treatments to combat, psychological placebo effects. We use, placebos because when you tell people that they're receiving a drug and they think it's going to work, a lot of times you see results that indicate that it's doing something. Okay, and placebos are just tablets that should have no effect. And therefore, you can compare the effect of the actual drug to maybe the effect of a placebo. Okay, and we have blinding. And this is to keep blinding prevents subjects and evaluators from knowing which treatments are being used. And these are all detailed a little bit more in the text. So do your reading, and I'll give you guys a chance to finish writing, and we'll talk about sampling. Yes, question.
So in terms of placebo,
Uh-huh.
the best way to define it is that it's effective in preventing bias.
Yeah. Yeah, so there's a known phenomenon called the placebo effect, and what the placebo does is it allows you to compare, it allows you to take into account the placebo effect into your analysis. So let's say if you give someone a drug, or if you give someone a tablet and you say this is going to help ease your headache, maybe they believe you, and for 1 hour they say it fixes my headache, okay, and then after an hour they're like, oh, but the headache has come back. So that might be the effect of the placebo, and you can compare that to an actual medication that might reduce a headache, and you can say, well, whenever we give patients the actual medication, they report that their headache went away for 3 hours, okay? And we might be able to say, well, maybe 1 of those hours is just from placebo effect, but the medication seems to have increased the reduction of pain for an additional 2 hours, so it seems that the medication is actually effective in increasing the amount of reported pain reduction or something, okay? So, well, that's all defined in there. I think you guys are probably familiar with the concept of a placebo, and it's not like, I'm not going to ask you to develop and design a complicated experiment here, but these are just topics and subjects you should be familiar with. So, it is quite remarkable, this placebo effect, and the power of suggestion, right? All right, let's talk about sampling and gathering data, or just maybe sampling, okay? So with sampling, this is the limited data part, okay? When we have a research question, the population, relevant population, the population is everyone that could possibly be relevant to answering this research question. Okay, so if we have a question, what is the average height of an American male, of a U.S. adult male, okay, and we'll just say adult is greater than or equal to 18 years of age. All right, what is the average height of a U.S. adult male? The relevant population would be all males in the United States, U.S., who are over 18 years old. Okay, that would be the population. That would be everybody who could be relevant to answering this question. With over 300 million people in the U.S., this number is probably over 100 million. There's a good number who are under 18, but you got over 100 million people in this population. Okay. And the only way to answer this question, what is the average, that would require the measurement of all 100-something million people, adding up all of their heights and then dividing by how many people you have. That's the only way to get the actual average to answer this question. Okay, so to get the actual average, we need to measure all 100 plus million people, million adult males, adult US males. You know, add up the heights and divide by how many we have. Okay. This is not possible in a practical sense. So instead of trying to measure the population directly, we deal with the sample, okay? So this is also what statistics is all about, okay? So we cannot measure the population. Population, let me just make this a little bit bigger. Okay, the population is too big to measure directly. So instead, we take a little piece out of the population, and this thing is called the sample. Maybe this is 1,000 people, okay? So maybe we select 1,000 people, okay? And we are hoping that these 1,000 people that we select are representative of the population, okay? Okay, we hope the people in our sample are representative we hope the people in our sample are representative of the population. Okay, so that's the sample, and we observe the sample. Okay, we can observe the sample and based on what we see in the sample, we will then make inferences about the population. Okay? Okay, and so this is the key fact, is that for our inferences to be valid, our sample must be representative of the population. Is that good? Can I go to the next slide? Okay, so how do we get a representative sample? Okay, and this is a tricky question. There's no guaranteed ways to get a representative sample. Okay, and that is going to be the crux of all studies that you do, is that maybe you get people to study, maybe you get experimental data and things like that. The question is, well, is the data I have representative of the population that I want to generalize these results to? You know, you're interested in, I don't know, people with bad kidneys or something, and you want to make conclusions that can be generalized to all people who have bad kidneys or something. Well, the question is the sample that you have representative of everybody with bad kidneys? And the answer is, we don't know, okay? There's no way to guarantee that you have a representative sample without knowing what the population looks like, and you don't know what the population looks like because the population is too big, okay? So there's nothing we can really do to fix this inherent problem, okay? It's just like, can we ever know that we've made the right decision about the future? And the answer is no. We don't know because nobody knows the future, at least as far as we know. No one knows the future, and so we do the best we can, and you know, we hedge our bets and things like that, but there's no guaranteed ways to get a representative sample, okay? We have a method that should, according to mathematics, should give us a representative sample, but it's not guaranteed, and that is simple random sampling. Should give us a representative sample. But not guaranteed. Okay. And the idea behind simple random sampling is that it's quite simple. You have a sampling frame. You start with a sampling frame, which is essentially just a list of every single person in the population. Okay, and then you randomly select individuals one by one from the sampling frame. Okay. And that's simple random sampling, often abbreviated SRS. And the concept is simple. You've got a list of everybody. You just pick people from that list one at a time. Randomly, okay? And you can do it by putting their names on slips of paper and you mix it up in a hat, or you can use a computer and using random generated numbers, things like that. Those are all valid ways to pick individuals from a simple random sample. The difficult part is getting the sampling frame, okay? We said we don't know everybody in the population. The population is too big. So how are we supposed to get a sampling frame, which is a list of everyone in the population? Was that your question, or?
I was gonna ask if like a sampling frame is like where you pick like a male between the age of like 10 to 12, and then like you go by like ages or something.
Oh, okay. That's a different. That's called stratified sampling, and we'll talk about that in a moment here. Okay. So simple random sampling. You start off with a list of everyone in the population. Pick from that list. Okay. The difficult part. So while it is simple in concept, the execution of simple random sampling is actually very difficult, okay? It is very difficult to get a good sampling frame. To get an accurate sampling frame. Yeah, it's very difficult to get an accurate sampling frame. For any, for any population larger than one institution. So for example, if we wanted to get all adult males over age 20 in the US, do we have a sampling frame like that? Not really, okay? We have the census, which is taken once every 10 years, and maybe we have enough age data to say, okay, well, the kids who are 15 years old then will now be over 20, but then that data is also outdated because some people have moved to the US since then, some people have died, and so that list of everyone is not going to be super accurate, and a lot of people are often missed on the census, such as people without permanent addresses, homeless people, things like that. So it's difficult to get a very good sampling frame, okay? If I just gave you the assignment, which I'm not going to, but if I said, I want you to get a random sample of people in Los Angeles County, nobody could do that. Or even the city of Los Angeles, you couldn't do that. Maybe you'd say, well, let's look at a phone book, but who here is listed in the phone book, okay? The phone book is not going to be a good list because, well, we live in 2015 and nobody uses the phone book anymore, right? So, excuse me, Pew Research tries to get good representative samples, and they have an entire team dedicated to just trying to get representative samples for their opinion polls and things like that. Their current method is random digit dialing. They have robots dial basically random numbers into the phone and hope that it rings and that someone picks up and the person answers. And that way they might possibly get people, but they don't rely on having phone listings or things like that. But not everyone has a phone. They say it's pretty good because about 98% of the U.S. is connected to a phone number, so they can get people that way. But it's hard. It's hard to get this. Okay, so simple in idea, difficult in execution. Okay, so that's simple random sampling. We have other ways to try to get a representative sample. Again, no method is guaranteed. Okay. One problem with simple random sampling is that it's random, and by random chance, maybe you get a sample that's not representative. And so to kind of combat that, we have what we call stratified sampling. Okay. So this is another method. Okay. So with simple random sampling, let's say you had a question, I don't know, that you think the gender of the respondent will have an influence on the response. So let's say it's you have a survey question and you want to know, have you ever experienced sexual harassment in the workplace? Okay, and the question, the answers to these questions are probably going to be associated with the gender of the respondent. Okay, and so if you do a random sample, and so let's say you did simple random sampling, you were able to actually get a good sampling frame. If you did simple random sampling, just from random chance, it is possible that your sample happens to have a lot more males than females. Okay, so the general population is about 50-50, but let's say because of the random sampling process, you happen to get 60% males and 40% females. Okay, therefore the answers to your survey may not actually be representative of the population because the random sampling process happened to give you a sample that didn't quite look like the population. So with stratified sampling, you say, well, I know the population is about 50% males and 50% females, therefore the sample I pick, I'm going to force to be 50% male and 50% female. Okay? So with stratified sampling, we eliminate one aspect of the random sampling process. We force our selected sample to have certain proportions of subgroups of our population. Okay, so for example, we might force our sample to be 50% male, 50% female. Okay, because simple random sampling might produce, something with different proportions just because it's random. You still select the males at random and you still select the females randomly, but you're forcing these subgroups to have certain proportions. And it doesn't have to be based on gender. It could be based on any other demographic characteristic. It could be on other things such as, we want to make sure we get some people who smoke and some people who don't, or whatever it is that you're looking at. And generally, when you do stratified sampling, you don't do it just for the sake of having a stratified sample, but you do it because you suspect that the results of that the research that you're doing might be influenced by whatever aspect that you're going for. Okay, if we're going to force 50% male, 50% female, it should be because we suspect that gender or sex has something to do with the research that we're doing. Okay, so there should be a reason. For stratifying your sample. Okay. The strata being the different subgroups that you have. Okay, you still have the same problems of simple random sampling requiring you have a list of everybody. If you're going to have 50% male and 50% female, you need to have a list of all potential males to be selected and all potential females to be selected. So it doesn't eliminate these problems, but it might force a certain amount of representativeness in your sample. Okay, so that's stratified sampling. We also have cluster sampling. This allows us to select samples that might allow us to get kind of random samples or kind of representative samples in a slightly easier way. Okay, so maybe in quote easier way to get a potentially representative sample. Okay, and the idea is the population has natural subgroups or clusters. Okay, and maybe it's difficult to get a list of everyone in the population. But relatively easy to get a list of clusters. Okay, then we randomly select clusters and then sample everyone, or do simple random sampling. Sample everyone in the selected clusters. Or perform simple random sampling within the clusters. So, for example, let's say you want to get the population is every single person who goes to church. Okay, so let's say the population is everyone who goes to church. Okay? And so it would be quite difficult to get a list of every single person who goes to church. But it's not difficult to get a list of all churches. Okay? So relatively easy to get a list of all churches. Okay? So what you do is you randomly select maybe 20 churches from this list. Randomly select churches from the list. Then perform simple random sampling within the selected churches. Okay. And that should give you a fairly representative sample of the entire population. Okay? So that's cluster sampling. The different, there's just inherent issues with sampling, okay? Let me just put this up here. All right, so issues inherent with all sampling. And that is, we have sampling error. And that's the fact that no one sample can be truly representative, okay? Be truly representative of the population. And the variation from sample to sample is known as sampling error. Okay, and then we have other sources of bias. Things like non-response bias. I don't know, what else, what do we have? Missing data, things like that. No matter what you do, you're not going to get a perfect sample, and so you have to take that into account and just be aware that maybe the conclusions you get are not perfectly representative of the population. Okay, why don't we take a break here?